Now we move on to look at section 1.8. And 1.8 deals with inverse matrices. And they say the title of the section is the inverse of a square matrix, so that's one clue. We have to have a square matrix in order for it to be invertible, to have an inverse. So before we get into all the ins and outs, one thing we need to define is what's called the identity matrix. So, to give you an example, a 2x2 identity matrix has ones on the diagonal, zeros everywhere else. A 3x3 identity matrix has ones on the diagonal, zeros everywhere else. And when I say the diagonal, I mean going from top left to bottom right. That's called the main diagonal, or often just referred to as the diagonal. So anytime we have ones down the diagonal, zeros everywhere else, that's called an identity matrix. So when we say that two matrices are inverses of each other, we mean that if we take those matrices and multiply them together, we get the identity matrix. Basically, they undo each other. If you think back to functions, when we take the composition of functions, they are in such a way that they undo each other. Well, this is similar to that ideal, except for matrices. If we take the product of inverses, then in a sense they cancel each other out in some aspects and give us this identity matrix. Or something that might make a little bit more sense. Multiplication and division are inverses of each other, inverse operations. If you think about taking 7 times 1/7, or 7 divided by 7, what do you get? You get 1. So basically you undid a 7 by dividing by it, or multiplying by its reciprocal. So we discussed the other day that not many matrices are commutable, but it does turn out that if we take a matrix times the identity that's that same size, if it is an identity, then when we multiply a matrix by that, we get itself out. Also, we can multiply in the other order. Just going back to what we talked about that being 1, think about if we take a number times 1, what does that give us? It gives us itself. So another way of looking at the identity matrix is a matrix that when we multiply that matrix times our given matrix, it gives us our given matrix. So it's kind of like multiplying by 1. So it turns out that the identity matrix is commutable. You can multiply the identity matrix on either side and you get what you started with. Now the book mentions a few theorems. One thing they say is that if a matrix has an inverse, if it's invertible, then the inverse is unique. There are not multiple inverses for any given matrix. So there's only one inverse for a single matrix. And they also give us a theorem. If we have a product of matrices, if A is invertible and B is invertible, Then if we take the inverse of the product of A and B, then we get the inverse of B times the inverse of A. And that might come up useful in the future. So they're going to lay out how to come up with the inverse of a matrix. And what they're going to have us do is set up an augmented matrix where we have the matrix we want to come up with the inverse of on one side and the appropriate size inverse matrix on the other side. So let's look at matrix A that is 2, -3, -4, 5. So let's put that in an augmented matrix with the same size identity. So this is a 2 by 2. So we want an identity matrix that's 2 by 2. If we can reduce this using row operations to where we have the identity matrix on the left, which basically is a reduced row echelon on the left, and then we have some numbers on the right, then what we come up with on the right side is the inverse of A. So if we take this augmented matrix and row reduce it till we have reduced row echelon on the left, that's the identity matrix, then that is our inverse. Now, quick note, if we come up with something on the right side when we row reduce it that is not the identity matrix, that tells us that A is not invertible. So A is only invertible if we can row reduce this augmented matrix and come up with the identity on the left. And that's true whether it's a 2 by 2, a 3 by 3, a 4 by 4, etc. So let's take this and let's row reduce it. Bring this over on another page. And let's see if we can get this in reduced row echelon on the left side. So the first thing I would probably do is I would say, okay, it would be nice if we had a 1 here. So let's divide that row 1 by 2, or you could say half of row 1 becomes our new row 1. So if I do half of this, I get a 1. Half of this is -3 halves. We have to do all the way across row 1, so half of this is 1/2. Half of that is 0. Now we need to get a 0 underneath our 1, so we need 4 times row 1 plus row 2 to yield our new row 2. So right now we're leaving the first row the same. So if I do 4 times this, I get 4 minus 4 is 0. 4 times this, minus 6 plus 5 is -1. 4 times that is 2 plus 0. 4 times that is 0 plus 1. Okay, now we have a -1 here. We need that to be a +1, so let's multiply row 2 by a minus. And that'll give us our new row 2. So we have a 1, a -2, a -1. So the only thing left to do is to get a 0 here. So to get a 0 there, we need to utilize this pivot. So if we had a positive 3/2, those would cancel out. So to get that, we would do 3/2 row 2 plus row 1 to give us our new row 1. So 3/2 times this is 0 plus that is 1. I guess we can go ahead and write down our bottom row because it's not changing. 3/2 row 2 here, so 3/2 times this is 3/2 minus 3/2 is 0. 3/2 times row 2, well, 3/2 times negative 2, that's negative 3 plus row 1. Is that minus 6/2 plus 1/2, so minus 5/2. Then for the last element here, that's 3/2 row 2. So minus 3/2 plus that, so minus 3/2. Notice we have the identity matrix on the left. So this, if we did that correctly, that will be the inverse of A. So, well, how do we know if that's the inverse? Well, we said that if we take a matrix and multiply it times its inverse, that gives us the identity. So let's check that. Let's take A, which was 2, negative 3, negative 4, 5. 2, negative 3, negative 4, 5. And let's multiply that times this inverse. And let's see if that gives us the identity matrix. So when we multiply, we're going to do row times column. So this row times that column. So 2 times negative 5/2. The 2's cancel, so that's negative 5. Multiply those together, and that's positive 6. So that gives us 1 there. Then the first row times the second column, 2 times that, the 2's cancel, so that gives us minus 3. Minus 3 times minus 1, that's plus 3. So that gives us 0. Now the second row, first column, minus 4 times that. The minuses cancel, the 2 and the 4 reduce, so that gives us 10. 5 times minus 2 gives us negative 10. 10 minus 10 is 0. Looks good so far. Second row, second column, minus times minus is positive. The 2 and the 4 reduce. 2 times 3, that's going to give us a 6. 5 times the minus 1, that gives us a minus 5. So yes, that's the identity matrix. So those two are inverses of each other. Now for time's sake, I'm not going to go and do that in the opposite order to show that that you can flip those and still get the identity matrix. But it should hold true if you do A inverse times A, that gives you the identity matrix. So that should work out. Now, let's mention a few things here. If we already mentioned that if we were to row reduce, and when we get here, get a row of zeros, if we come out with a row of zeros, then our matrix is not invertible. Now they have a theorem on page 104 that says if you have a 2 by 2 that the shortcut for determining the inverse of a 2 by 2 is taking what's called the determinant of A, taking 1 over that, and then moving elements of matrix A around. So this is what's normally the second row, second column element. So in this case, this is 1, 1, row 1, column 2, row 2, 1, row 2, column 2. So this would be 5. This would be this 2. On these, we take the opposite signs. But they stay in the same place. This is still row 1, column 2, still row 2, column 1, but we take the opposite signs of those. So those would take the opposite signs, those flip. Then once we do that, we could multiply times 1 over the determinant of A, and they define the determinant of A to be the product A11 times A22 minus A12 A21. So a shortcut for a 2 by 2, let's come up with this product for ours. A11, A22, so 2 times 5, A12, row 1, column 2, A21, row 2, column 1. So determinant A is 10. Minus times minus times minus makes a negative. 3 times 4 is 12. So we get the determinant of A to be negative 2. So if this theorem works, then 1 over negative 2 times what we get when we manipulate our matrix. So swap the 2 into 5. Leave these in that place, but change their signs. So if we multiply this matrix times that scalar, 5 times negative 1/2, 3 times negative 1/2, 4 times negative 1/2, 2 times negative 1/2. Notice that's what we got when we calculate our inverse matrix using our row operations. Now that works for a 2 by 2 matrix, but if you get larger than a 2 by 2, then you run into trouble. But one thing that we can apply to other size matrices is notice that if the determinant of A equals 0, this is undefined. So A inverse is undefined. Now we've only defined determinants for a 2 by 2 matrix. The way we get a determinant for a 2 by 2 matrix is to multiply along the main diagonal, multiply across this diagonal, and subtract those results. So 2 times 5 minus negative 4 times negative 3. But it turns out you can get the determinant of any square matrix. So if the determinant of a matrix is 0, then it's not invertible. So that's another way to check to see if a matrix has an inverse. If we have a 2 by 2 matrix, if we find the determinant does not equal 0, then it's invertible. If the determinant does equal 0, then it's not invertible. So that's a little neat trick that we can do. because sometimes it takes us a while to go through the row reduction, and sometimes we end up with messy numbers. But if we know right off the bat that when we take our determinant that we're going to get 0, then there's no point of even going through that, because we know there's not an inverse. It's non-invertible. One more definition that let's mention from this section, or terminology, is the phrase row equivalent. And matrices are said to be row equivalent if we can attain, say this is matrix A and this is matrix B. If we can attain this matrix from just doing some row reduction of that matrix, or if we can do any allowable row operation on this matrix and end up with that one, then they're said to be row equivalent. For example, if we have the matrix this, I don't know if you'd want to or not, but if we were to swap those are said to be row equivalent. We can attain this matrix from that one just simply by swapping their rows. If we wanted to get a 1 here, we divide each of those by 2. So we can attain this matrix from that one. So they're said to be row equivalent. We could get a 0 here if we wanted by multiplying row 1 by minus 4 and adding that to row 2. So if we do minus 4 plus that, we get a 0. Minus 4 times this plus that, we get a 0 here. All of these matrices are said to be row equivalent because we can attain 1 from doing row operations on rows. We can get 1 from the other. So all of these are said to be row equivalent. Now I mentioned that to mention this. Theorem 6, which is on page 111 in our book, is called the summing up theorem. And they give 6 different statements, and they say that all 6 of these statements are equivalent. Basically, if one of them is true, then all of them are true. So the first statement is A is invertible. So basically, if A is invertible, then the other 5 statements are true. If A is not invertible, then the other ones may not be true. Or, I'm sorry, then all of the other ones are not true. The second statement, it says that the only solution of the homogeneous equation is the trivial solution. The only solution to the homogeneous is the trivial solution. Now, if you think about that, in order for A to be invertible, then when we take A in augmented form, we have to come up with the identity matrix on the left. Now, if we can do that, think about what would happen if we solved the homogeneous system with A. Then we would come up with that. If we come up with this, that means we only have the trivial solution. X of 3 is 0, not arbitrary. X of 2 is 0, x sub 1 is 0. So if we have pivots in each column, then the homogeneous system of equations only has a trivial solution. If we have pivots in every column, then we can find the inverse. Statement 3. The system AX equal B has a unique solution for any B that we have. Or we could say for every B. So again, basically, if we have an augmented matrix, but this time we don't have zeros on the right. Once we row reduce, x1, x2, x3, none of those are arbitrary. So x sub 3 is whatever that last number turns out to be. X sub 2 is whatever the last turns out to be. X sub 1 the first, once we row reduce everything. So if A is invertible, then the homogeneous and the non-homogeneous system have unique solutions. If A is invertible, it's row equivalent to the identity matrix. It's row equivalent to the identity matrix, which is the same size of A. So if A is 2 by 2, then it's row equivalent to a 2 by 2 identity matrix. If A is 3 by 3, it's row equivalent to a 3 by 3 identity matrix. And we saw that we had not defined row equivalency yet, but we saw that here when we took A with an augmented matrix with an identity here, and we row reduced that, we came up with the identity matrix on the left by elementary row operations. So if we can come up with something through elementary row operations, we define those to be row equivalent. This matrix is row equivalent to the identity matrix. Hence, all of these other things are true. Statement 5. When A is in row echelon, A has n pivots, and keep in mind A is an n by n matrix. So A has as many pivots as it has rows and columns. If A is 2 by 2, there are 2 pivots. If A is 3 by 3, there are 3 pivots. So every variable is a pivot. And then statement 6, we mentioned this also earlier, the determinant of matrix A is not 0. If the determinant of A is 0, then it's not invertible, which means that there is not just the trivial solution to the homogeneous. There is not a unique solution to the non-homogeneous system. A is not row equivalent to the identity matrix, and there are not n pivots. So if you took A, row reduced it, put it in row echelon, or reduced row echelon, you would have more columns than you have pivots. So basically you would have a 0 row. So that pretty much sums up all the properties and ideas that we need to deal with in section 1.8 about finding inverses. So you're pretty much going to be row reducing matrices with the identity matrix, trying to come up with the inverse of A. So if we take that, row reduce it so we have the identity on the left, and what we have on the right is the inverse of A. If we can't get the identity on the left because of one of these things, basically if we come up with a 0 row, then A is not invertible. So let's see. Let's look at an example. I hope I copied it down correctly. If we looked at this, if we wanted to see, if we wanted to find if it is invertible, and if it is invertible, what the inverse is, since it's 2 by 2, we could go through a shortcut and we could say, well, what is the determinant? If the determinant equals 0, then it's not invertible. So to get our determinant, we get that product minus that product. So -1 times -12 minus 2 times 6. That's 0. So there's no inverse to this matrix. Now we can verify that real quickly by looking at our row operations. If we wanted a positive 1 here, we would do the opposite of row 1. So our new row 1 would be this. If we wanted a 0 here, we would need this to be -2. So -2 times R1 plus R2 would give us our new R2. So -2 times 1, so -2 plus 2 is 0. -6 times -2 is 12. -2 times this is 2. -2 times that plus that is 1. And I did this wrong here. -1 times -2, that's 2 plus 0. I said it right, I just wrote it wrong. Notice we have a 0 row. So we're not going to be able to come up with that. Hence, no inverse. Basically, we took matrix A. It does not have as many pivots as it has columns. It doesn't have an inverse. So let me go back and look at it. There are not n pivots. So if this is false, all the other things are false. So A is not invertible. So it would be a very good idea to keep all of those lists of 6 items. Keep those in the forefront of your mind so that if we find out one of these things, we can understand, well, what does that imply about other aspects of our matrix or our system? So I'll give you a list of several of those to do for homework, and then we'll take a look at those when we get back.